Hello and welcome to this video. In this video we're going to continue on with this topic of further mechanics by looking at this idea of simple harmonic motion. Now this is usually shortened, so instead of writing out simple harmonic motion all the time, I'm usually going to shorten it to just SHM. But what exactly is simple harmonic motion? So far in this course we've looked at linear motion, which was just motion in a straight line. We've looked at projectile motion, which is where we have some sort of arc that a projectile would follow. We looked at circular motion recently, where things move in circles, and now we have another form of motion called simple harmonic motion. Now, simple harmonic is kind of the two words that will always remind you what's happening here. So the word simple in this case could be replaced with the word real in some instances. We use the word simple harmonic motion because we're neglecting forces. So we're neglecting forces like friction or basically any resistive forces, but for the most part it's just going to be friction. So we're neglecting friction, and that is the simplification that we make so that all of these equations work. So all of these equations neglect friction entirely, which is the case for simple harmonic motion, but not necessarily for real harmonic motion. So if we had something that was undergoing real harmonic motion, we obviously always have friction present, but in a perfect case, we wouldn't. And so we'd say that these equations would be an approximation of a real harmonic oscillator. Now, harmonic, we've heard before in waves, where we have standing waves, and we always said that waves were sinusoidal. We always described them as being a transverse wave where it went up and down. And so harmonic just means that we have a repeating effect. Okay, so this is just going to be repeating motion. So it's something that is going to have no friction and consistently follow the same path. And if it's got no friction, it's got no forces that are going to dissipate any energy, and hence it will go seemingly forever. Obviously in real life we can never get something that will move in the same way forever, because that would be requiring infinite energy, which we can't get. But we can then take this whole idea and say, okay, let's put an example on this. And the most common example that you will look at is a pendulum, or a simple pendulum. Because a pendulum which is just, for anyone who's unfamiliar, is just, let's say this is my start line, and I have a string here, and I have a ball attached to this string. And this ball, I'm just going to let go, and it's going to swing back and forth. Okay, and this ball will swing back and forth, and it will just continue to swing back and forth. If we have no friction on it, then we're always going to get the constant back and forth motion, and hence this would be a harmonic motion. Now we can refer to this also as a harmonic oscillator, because it is going to oscillate between these two positions. And so just like a wave will usually oscillate between two positions, so will this harmonic oscillator. Now we need to put a more strict definition on this, because this is all kind of, okay, we have this kind of motion that does this, but how can we tell if something is undergoing simple harmonic motion? We need a small rule that just allows us to differentiate between circular motion and simple harmonic motion, or any other type of motion. And that rule is on your formula sheet, and it is written like this: that the acceleration at any point along this path is always equal to negative the angular frequency of these oscillations multiplied by the displacement. Okay, now this is how it's written, but the actual thing that you would have to specify is that the acceleration is always proportional to minus the displacement. So acceleration is directly proportional to the displacement. Okay, now this negative comes, this negative sign here comes because the acceleration and the displacement are both vectors, so the acceleration will always be in the opposite direction to the displacement. Okay, and so that's your second part. So the acceleration is directly proportional to the displacement, but always in the opposite direction. Okay, there is only one position really where this isn't true, and that would be if it was dead in the center here, because you'd have 0 displacement and 0 acceleration also. But you can say that acceleration is directly proportional to the displacement, and the acceleration will always be in the opposite direction to the displacement. Let me try and convince you of this if you're not already convinced. Let me get a larger diagram of this. Okay, so let's say we have this pendulum here. Okay, and this is our origin point, and we know that this is going to swing through some sort of curved path. At this point here, we know that it's going to begin to accelerate in this direction. Okay, and in fact, everywhere along this side, it will have accelerated in the opposite direction. So it's going to accelerate, if we just put it as horizontal and vertical, it's going to accelerate in this direction, because as it starts to move in this direction to begin with, it's slowing down, which means it's accelerating backwards to the way it came. And so for this whole thing, if we define this side, so we define this direction to be positive, everywhere where the displacement is on the positive side, the acceleration is pointing to the negative. So acceleration is always negative when the displacement is positive. And if I were to then have a look at the other side and have this, when the displacement goes negative, it's always accelerating to try and go back that way, because it will slow down when it first comes, and then it will accelerate back this way. So really, if the acceleration is in the negative direction, you must be displaced to the positive direction. And if you're displaced to the negative direction, then your acceleration must be in the positive direction. And this is why this works. Now, this specific omega squared here is just the constant of proportionality. And we've seen before now in circular motion that we could write this as 2 pi over t, or we could write it as 2 pi times f. So this is just the omega squared here. And we get this from when we do forces and we balance forces, and we get an expression for acceleration, and we always find that it comes back to this form as long as there is a simple harmonic motion present. And that's why this is our definition of a simple harmonic motion, because it doesn't matter if we where we start or where we do this. If we calculate an expression for the acceleration, we always end up with this idea that the acceleration is proportional to negative the displacement. Now, pendulum isn't the only example you're going to encounter in this. The pendulum is probably the easiest one to probably wrap your head around, since you've probably almost definitely seen a pendulum. The other one that we will look at is a mass spring system. And this is just the case of if we have a spring here and we attach a mass on the bottom of it, and then we pull the mass down and let go, it's just going to oscillate up and down and keep bouncing. And because when it goes up, it might be in the positive direction, but it's actually accelerating downwards, then we have this simple harmonic motion expression will appear again in that case. So what we're going to do from here, this is our idea of how we're defining simple harmonic motion. We're going to look at how do the graphs of displacement, velocity, and acceleration look in this case? How does the energy change when we do this case? What is so specific and special about this case of a pendulum and a mass spring system? And then we're going to look at what happens if we actually put in some forces. Do we end up with larger oscillations? Do we end up with smaller oscillations? What exactly happens? So this is going to be the topic of simple harmonic motion. Thank you for watching.